Okay. All right. Okay, so where were we? Okay, so let's let me just mention what happens when M is three-dimensional. So if M is three-dimensional, then K plus 2, Betty K plus 2 is only going to be interesting when K is 1. And so the statement is only really saying something about 1 minus 1 equals 0. That's pi 0 isn't a group, but the same argument gives, the same argument says that the set pi 0 of path components of the space of flat connections is infinite. As long as M is orientable so that it has a top third cohomology class. If you had a non-orientable manifold, then you just have 0 on this side. But the statement is, for any orientable 3-manifold, the space of flat connections, flat unitary connections, I think the rank has to be at least 2 for the bundle. It's going to have infinitely many path components. That's the statement. Okay, so let me say a little bit about how this is proven. So the idea of the proof is to, well, so we're going to think about some, it's really a family of representations, a map from a sphere into the space of unitary representations. So I'm going to be thinking about this map, the boundary map for this vibration. So I have sphere mapping into here, and I want to study the associated bundle. So we have an associated bundle, might call E rho K, and it's basically a family of these bundles over here, parametrized now by a sphere. So this lives over SK cross M. It's just defined the same way, just tack on a sphere. So the fundamental group now, the action on Cn changes as you move around the sphere, depending on the representations that you see. Okay, so we get this this bundle, and what we want to do is basically put a connection on here, and so if you fix a point in the sphere, you get that flat bundle over there, which has a canonical connection. So you have a family of connections on here defined in the M direction. And so what you want to do is extend that to a family, extend that to an honest connection that's smooth over the whole base and then flat in the M direction. So there's something subtle about this because this is a map into an algebraic variety that's singular. And to get a smooth connection like that, the first thing you're going to need is that the various connections, the various flat connections over there are in some sense changing smoothly as you move around the sphere. So that's the first thing that we have to deal with. So there's a very general result that it's really Tom came up with this argument, the argument that proves this. So if we take any real algebraic variety, just sitting inside Euclidean space, and M, the smooth closed manifold, then every map from M into X is homotopic, well, inside X to a C infinity map. So by a C-infinity map, I just mean M is mapping into X, which sits in Euclidean space, and so you just think of it as a map to Euclidean space and ask, is it smooth? So the theorem is that you can deform any map to make it smooth, no matter how bad the singularities in the variety might be. And well, maybe I'll just say a word about how this is proven. The idea is to embed X as the singular set of a larger variety. So it's a little trick that any algebraic variety is the singular set of some larger variety. And then you can resolve singularities in that larger variety, and that sort of reduces you to the case where the variety you're looking at is a divisor with normal crossing singularities, and that can be sort of handled by differential geometric means. So, well, that's just an indication of the idea. Okay, so the idea now, we can, up to homotopy, just assume that this is a C-infinity map, and then that family of flat connections over there is varying smoothly as I move around the sphere. And then just a partition of unity argument says you can extend that to a connection defined on the whole bundle. So it's not going to be flat in the sphere direction, it's just going to be flat in the M direction. So you get a connection on this family of bundles flat in the M direction. And then what do you do with that? Well, you look at what Chern-Weil theory tells you. So if you take C K of this, oh, K is a bad letter, I guess, CL of this bundle, that's going to be, well, so you'll take the curvature form of your connection and plug it into the Elf symmetric polynomial. This is just working rationally here. And so the claim is that that's going to vanish once you go above the dimension of the sphere you're working with. And basically the point is, you can write this in local coordinates. It's going to have some components in the M direction, components in the sphere direction. And once all the terms in this polynomial are bigger than K, everything's either going to be killed off from the flat directions here, or it's going to have sort of too many directions in the sphere, and it'll just vanish because there's no cohomology above dimension K in the sphere. So that's just an argument in local coordinates. You just write it out. Okay. So the idea is then that C K plus 1, C K plus 2 all vanish. And so now this is giving you constraints. What this is saying is that if I have a bundle here, so this is just classifying bundles. So if I have a bundle here that has non-trivial high-dimensional characteristic classes, it's not in the image of this map. And once your bundle has large enough rank, you can build whatever characteristic classes you want rationally, basically just because the Chern character is an isomorphism. So what that gives you is a bunch of classes over here that are not in the image of this map, and, well, that map is the same as this map, so we have a bunch of classes that are not in the image of this map, and then they survive into here. So the conclusion is that we get classes in here, which is roughly like the K-theory of the manifold, the complex topological K-theory of the manifold, which map non-trivially to the space of flat connections. And so that's where this lower bound on the homotopy comes from, and you have to trace through the dimensions to see, exactly which which cohomology classes contribute to what homotopy group, but just sort of tracing through. And so one thing about these classes is that they're sort of, I don't know, tame in some sense because they're all just coming from the gauge group. So one could ask, are there more exotic classes here that aren't just in the image of this map? And so the examples that I want to give, this example with the Heisenberg manifold, is a case where there are lots of classes in here that do not arise in this way. They don't come from just the inclusion of a gauge orbit. I mean, this map here is just including a gauge orbit into the space of flat connections. All right. So the timer isn't on. So whoops. Okay, great. So in order to get these sort of more exotic, in some sense, classes in the space of space of flat connections, I need to use some more homotopy theory. So I want to explain a little bit about what I call stable representation theory. So the idea here is to look at the spaces of all unitary representations as n varies and consider that as one object and apply some ideas from homotopy theory to that object. So I'll explain what that means. Okay, so we're going to study the topological monoid. So call this rep of gamma. So it's just, as I was saying, it's all these representation spaces put together. So it's a monoid in the sense that it has a operation, an addition operation, so simply block sum of representations. So if I have two unitary representations, I can take their block sum. That's a continuous operation. It's also worth pointing out that it's homotopy commutative. So there's a canonical, well, you can choose a path of representations which flips the order here, just conjugating by a rotation matrix. Well, conjugating by a rotation matrix flips the order, but that matrix can be connected by a path to the identity, and that gives you the homotopy. So this is a topological monoid, and so, well, one can feed it into what's called an infinite loop space machine. So I'm not really going to use anything about that, but let me just state a definition. So this is what's called, my advisor named this deformation K-theory. Maybe that name will become more sensible in a minute. So this is the homotopy group completion of this monoid, rep gamma. So, well, if you like this sort of language, you can think of it as the loop space of the bar construction of this monoid. But again, it doesn't really matter. I'm going to give a more explicit description of what I need to know about this, which is basically just its homotopy groups. So some of the results that I'll explain in a minute rely on thinking of this in a homotopy theoretical sense. So in fact, so tensor product, you also have tensor product of representations. So this gives, so this is sort of an addition operation. Tensor product is sort of a multiplication operation. It gives a multiplicative structure. And so, in fact, Tyler Lawson showed that this thing it has sort of a structure of a ring up to homotopy. I could just say it's a ring spectrum. But you should just think that it's a space whose homotopy groups actually form a ring. And roughly the idea is that that ring structure is coming from taking tensor product of representations. Okay, so here's the more explicit way of thinking about this. So if I just look at the homotopy groups, of this thing. So usually it's hard to give any kind of a concrete description of the homotopy groups that come out of this sort of homotopy theoretical process, except for pi 0. So pi 0 is really just the Grothendieck group of the monoid of components. So I could take the connected components of this thing, those form a monoid, and when I group complete like this, what I do to pi 0, the connected components, is simply taking the Grothendieck group. So it's just the group completion. But on higher homotopy groups, usually it's more complicated. But in this case, it's not very much more complicated. So what you get is the following. So it's the Grothendieck group of maps from a K-sphere into this monoid. So what do I mean here? Here, this is unbased homotopy classes. So you should think of an element here. I'm gonna have to kill something, but you should think of an element here as just a formal difference between two homotopy classes of these k-dimensional spherical families of representations. So it's just a Grothendieck group. So just formal differences, and I have to kill the constant maps. So in here, I have some maps that are just constant, and those we just kill. One way to think of that is, if you look at the vector bundles associated to these families, if the families are constant, that vector bundle is not going to be very interesting, and so we're just going to throw that data away. So the name deformation K-theory, you're supposed to think of classes in here as sort of coming from deformations of a representation. And then this theorem is sort of saying that what you're seeing are spherical deformations in some sense. Okay, and in fact, I can say a little bit more than this. Turns out, I mean, an element in this Grothendieck group looks like a formal difference between two representations, but actually, when you kill the constant maps, every class is represented by a single representation, or a single family of representations. So what is that saying? That's saying that somehow up to homotopy, I can get rid of that minus sign. So I'm trying to subtract off formally a representation, and up to homotopy, you can do that. Well, I'll sort of sketch how that goes. Gives a little bit of the flavor of what's going on in this picture. So why can I do this? So I have this spherical family of representations. It's a map from a sphere into the space of representations. And I want to sort of, I'm thinking of subtracting it off, so I want some sort of formal inverse to this. I want to say that instead of subtracting it off, I could just add on some other representation. That's the idea. So what other family of representations could I add to this to get something that's trivial? Well, it's a map from a sphere, so I can just flip the sphere. So if k is 1, just think of the loop going the other direction. Just negation in the homotopy groups, basically. So I can take the block sum of those representations. So that looks like this. But now what I can do is I can tack on some trivial representations. So I can compose with a constant map. I'll just write constant map. It really means the constant map at one of those representations. So now you should think you've got your sphere, and on one half of the sphere you see this guy, and you're really pinching the sphere, and on the other half you see a constant map. And that constant map, so again, think of pinching the sphere, so whatever value you get at that point from this representation, from this family of representations, just extend by that constant map over the rest of the sphere. And then here I'm going to do it in the other order, like that. And now this is exactly the same as if I did this, this, and then C psi k bar. So this, again, means putting one on one half of the sphere and the other on the other half. These are exactly the same map. And now I can use the rotation trick. So up to homotopy, I can rotate these guys like that. And then now, what do I have? I've got psi k composed, with its inverse in homotopy. And then, well, doing C twice is still constant. So what does this look like? It just looks like C. This cancels out to just C and C, so this is now constant. So I've canceled this out up to constant maps, but I was killing constant maps here. So what this is saying is that every representation has sort of an honest inverse in this monoid up to constant maps. And so, if I see something like psi k, rho k minus psi k, I can instead write this as rho k plus the reverse of psi k. So this is nice because it means if you can compute this this object by using some sort of homotopy theory, then you have something explicit. You can say something explicit because every class that you've computed there is really just coming from a family of representations, and it's something you can kind of get your hands on. Okay. Are there questions? Okay. So before I was talking about the holonomy fibration, and we had this description of the boundary map. And so that map has a sort of refinement in this stable picture where I take into account representations of all ranks. And in this context, it sort of fits into the an idea from homotopy theory called assembly or co-assembly. So the rough idea there is that if you have some invariant of a space that's well-defined up to homotopy, so here we're just, think of taking a manifold, take its fundamental group, and produce this representation theoretic object. It only depends on the fundamental group. So given some sort of homotopy invariant object like that, you can compare it to sort of the closest homology or cohomology theory. And in this case, the closest, well, the way you get the closest homology or cohomology theory is by looking at what happens when you plug in a point or plug in the trivial group. When you plug in the trivial group here, you're just getting, well, I'm sort of doing a based version, and for the trivial group here, what would I get? I would just get the integers. That doesn't look so good. So I need to sort of do the unbased version to really make sense of what I'm saying. But anyway, the upshot is that when you look at the sort of closest cohomology theory, it is topological K theory. And there's a natural comparison map going from this object to topological K theory. So it's just a souping up of what I was saying before. So this I usually call this the topological Atiyah-Siegel map, because Atiyah and Siegel wrote some papers about this sort of for finite groups. So basically all we're doing here is we're taking this monoid of representations and mapping to the space of maps from disjoint union over n, I guess B pi 1 m, really. And it's just rho goes to that map B rho I was talking about before. And then this induces a map from this deformation K-theory object. Well, so this thing maps into BUN, that's classifying vector bundles. And when you feed this monoid into the same machine as I was talking about before, you get out topological K-theory. You get out the group completion of the set of vector bundles. So you get the K-theory of So we should think of M being aspherical so that this is just M again. So this has an explicit description where a spherical family, so every element here is just represented by a single spherical family, and all you do is take that vector bundle that I was describing before. So it's very concrete, but it also fits into a kind of general framework. And so there's sort of a theme with these comparison maps that when they fail to be an isomorphism, when the homotopy invariant theory is sort of different from the associated homology or cohomology theory, somehow the failure is geometric. So maybe the most well-known example of this is in surgery theory, people look at an assembly map, and that assembly map tells you about the classification of manifolds. So classifying manifolds within a homotopy class, classifying manifolds up to homeomorphism within a homotopy class. So there's some sort of geometry that's exposed by studying these kinds of maps. And so here, based on what I was saying earlier, the sort of geometry that's coming out is the geometry of the space of flat connections, because this map looks just like that description I gave before for the boundary map of the holonomy fibration. It's just that we've kind of souped it up to take all ranks into account at the same time. So, okay. So, let's see. So, I want to say a little bit about how we actually compute these things. And so this is basically due to Kaehler-Lawson. So he shows that there are spectral sequences. So sort of a homological algebra device for computing these guys. So what do? You look at the space of irreducible n-dimensional representations. It's really the one-point compactification. So this is like Hom gamma. Sorry. Gamma was pi 1 of my manifold here. I could have written just gamma everywhere, I guess, but let me just think of the fundamental group of a manifold. So I look at all the irreducible, so the irreducible representations, the one-point compactification you can think of as just collapsing away the guys that are sums of lower dimensional representations. So that's what I mean by the irreducible, just collapse the reducibles to a point. So you can look at the homology of this, and first Lawson constructs a spectral sequence which produces, well, it produces something about the homology or the homotopy of the moduli space. So, it's this homotopy group completion of the monoid that you get by looking not just at Hom, but at the moduli space under conjugation, so the Betty moduli space. So you can think in good cases, the example that I'm going to give with the Heisenberg manifold is maybe like the worst possible case, but in good cases, you could think of this thing here as being just homomorphisms from pi 1 of the manifold into the infinite unitary group. That's what happens like for a surface. So that's the sort of thing that one's able to compute from the irreducibles. It sort of makes sense. You can understand the irreducible representations. There's some way of putting that information together to understand the whole moduli space. And this is one place where the unitary is really important because all unitary representations decompose into irreducibles uniquely. And then there's a second spectral sequence which ends up at this deformation K-theory object. So the guy that we're talking about here. So what this is saying is if you can understand the homology of the space of irreducibles, you can often get information about these spherical families of representations. And this really uses the full strength of the homotopy theoretical structure here. In particular, this business about ring spectrum. So it really uses the tensor product structure in an essential way. All right. So now, the last, what do I have, 10 minutes? 5 minutes? 8 minutes? The last little bit here, I'm going to talk about the Heisenberg manifold. So this is maybe one of the, given what I've said so far, this is sort of, in some sense, the simplest application because for what I'm going to say now, I don't need to use the ring structure anymore. Everything I'm using about the ring structure is just embedded in what Lawson did. So what's the Heisenberg manifold? So first, the Heisenberg group. It's just this group of upper triangular integer matrices. And, well, that sits inside R3, thought of as upper triangular matrices with real entries. And then I can take the quotient, so I guess I'll call it N because it's a nil manifold. It's just this R3 modulo H. Just sitting inside there as a discrete subgroup. So N is a compact, orientable 3-manifold. So from what I was saying earlier, we know that pi 0 of the space of flat connections on say a trivial bundle over N has infinitely many components. Well, at least if N is, I want to think about bundles of rank bigger than 1. It's just a 3-manifold, so you don't need much rank to make it work. So there are infinitely many connected components, but the stuff I was saying earlier, those cohomological bounds don't say anything more because there's no cohomology. This is already using the 3-dimensional cohomology class, the top class, and there's no higher cohomology to give you information in higher degrees. So in order to get more information, I'm going to study this map here. Okay, so the real, in some sense, the real work behind this example was something that Lawson had done a while ago, and just with this framework, we can now extract something about flat connections from what he did. So using work of Lubotsky and Majid, I'm never sure how to say that name. So Lubotsky and Majid studied the space of irreducible representations of the Heisenberg group, and it's sort of crazy, sort of a crazy space. And so what they were able to, or what Lawson was able to extract from their work using these spectral sequences was that this thing is infinitely generated. Let me put a K here. It's infinitely generated free abelian group for every K greater than or equal to 0. So there are just tons of these spherical families of representations that are, linearly independent. So what's the consequence about flat connections? So it's a little bit hairy to state because there are infinitely many components, and so somehow one doesn't, at least I don't, I don't know how to kind of distinguish between the different components in some sense. So I have to sort of take all the components into consideration in order to make a statement here. So it's kind of strange definition. I'm going to let pi k tilde of the space of flat connections, this three-manifold, be the direct sum of all the homotopy groups for the various components. So I'll take the direct sum over some set of representatives for these infinitely many path components and just add together all those homotopy groups. So then, well, for k at least 1, it's already said what happens for pi 0. For k at least 1, the rank of this group the rank of this group, so it depends on the dimension of the flat bundle that we're considering, the trivial bundle, but it grows without bound as n goes to infinity. So roughly the idea is this is infinite rank. You might not be able to see that whole infinite rank for a particular, if you restrict the dimension of the representations to a particular level, but if you let this grow without bound, you'll start to see it all. And so let me just say a word about where this result is coming from. So we have this map here. The domain now is this huge infinite sum of copies of Z. And, well, this is just now the K-theory of some three-manifold. So this is just a finitely generated abelian group. It's the cohomology of this manifold is pretty small, actually, so it's just a pretty small group. And so this map has a huge kernel. Okay, so this map has a huge infinitely generated kernel. But as I was saying before, this map looks just like the boundary map for the holonomy fibration. Basically the same sort of description that I was giving for that map before. And so what this is saying is there are tons of classes in the homotopy of the representation space. So remember, each class in that kernel is represented by just a single spherical family of representations. And when that family dies over here, so if it's in the kernel, it's dying here, that's basically saying that it goes to 0 under the boundary map of that holonomy fibration, and so it's hit by some class coming from the space of flat connections. So everything, this kernel is basically surjected onto by pi k of the space of flat connections. Now, again, the business with rank here is that you can't be sure for a particular rank that you're seeing the entire kernel, so you have to let the rank go to infinity in order to be sure that you're seeing the entire kernel. So what's the upshot? So this is very different from what happened in 2 dimensions, where in 2 dimensions we saw that the space of flat connections was highly connected, and there was a stratification, the Yang-Mills stratification, which is a stratification by submanifolds that are high codimension. So since this space has these crazy homotopy groups, it means that, well, you can still write down the Yang-Mills functional, and it does still have a well-defined stratification, but that must not be a stratification by submanifolds of high codimension. So I don't know. I don't know what that means exactly, but it's sort of intriguing. So I think I'll stop there. So it is an aspherical manifold because we're just, the universal cover is just this R3. So pi 1 of n is H. Yeah. Yeah. So we're just looking at, yeah. So B of H is n would be another way to say it. Yeah. Yeah. Mm-hmm. Yes, oh, absolutely. So this computation, as I was saying, it comes, so there's this book by Lubatsky and Majid where they have an example in there where they study the Heisenberg group in some detail. And so Lawson was able to extract from what they say about irreducible representations, he was able to extract the homology and then feed it into these spectral sequences. Yeah. So there are lots of three manifolds for which, like, for example, one can think about flat three manifolds, so three-dimensional crystallographic groups. And there are not very many of them. Most of them are much better behaved than this. I have some sort of preliminary computations for what's called the Hunch event manifold, where you see kind of somewhat similar behavior. I mean, the kernel is finitely generated now, but still you get these classes in the space of flat connections that don't come from just a gate orbit inclusion. So I don't think, I mean, this isn't a completely general phenomenon, but, well, I don't know. Right, yeah. Yeah, right. So it's very plausible that, you know, there should be generalizations of this computation, but you need to be able to compute the irreducible representation. So, yeah. Yeah. Oh. Yeah. So I guess if you just switched to the inverse, yeah, I guess.